this computer, share screen, share. Oh, that's not right. Move that up a little bit. Ah, I just lost everything I had. I didn't save it because it crashed. Where we've gotten so far, we had an inductor with an unknown VL. We had a capacitor with positive pointing up with a voltage of minus 100 volts. We knew the current through the resistor because this is series, and this was 0.5 amp. Since you had 0. And I'm going to put the resistor voltage going. No, I didn't. I put it going down. So I've got a 250 ohm resistor with 0.5 amp gives me, yeah, because passive sign convention, what I'm doing passive sign convention, 125 volts. Then I'm using KVL around the loop. So going clockwise, starting with the resistor, I'm going from plus to minus. It's a drop in voltage, so minus 125. Be careful with your signs here. Minus VL, minus negative 100 is plus 100 equals 0. And if you get your signs right, you'll come up with the right answer. So VL equals negative 25 volts. Negative 20. Where is it? Right. 25 volts. So if I want to find DVL, nah, don't do that. DIL dt, the rate of change of current at t equals 0 plus, that's going to be VL of 0 plus over L. So our VL of 0 plus was negative 25 divided by 5 henries gives me negative 5. And that's the rate of change of current, so that has units of amps per second. Okay, we got this. That's all one equation. Now remember what we were trying to solve for was we had A1 plus A2 was IL of 0 plus. And that was given to us. What the heck was that? Go back to PowerPoint. I'm going to have to do this.
It was 0.5 amps.
Yeah, I know. I need to get my PowerPoint open anyways. Oh, 2-second work. Okay, 0.5 amps. Thank you. Let's get that open. And I was close. I was about right here. I was on number 10. This is 0.5 amps. And then we had SA1, which is S1A1, which was negative 10 A1 minus 40 S2A2 equals this DIL of 0 plus. And we got a number for that is negative 5. Now I stick that into my calculator. I do a little bit of calculator magic. Learn how to solve systems of equations on your calculator. It saves you a bunch of time. And basically what I come up with at that point is A1 is 0.5. There's a point in there. That's a point. And A1 has units of amps. A2 is 0, also has units of amps. So if we go back and look at the form of our equation, it looked like this. IL of t, A1 e to the S1t, plus A2 e to the S2t. And since it's a current, it's in amps. And I plug in all the numbers that I have. IL of t equals A1 is 0.5. E is E. S1 was -10. T is my variable. A2 was 0, so that goes away. There's the expression for the current as a function of time. Kind of long problems and hard to do. They're so much easier to do on the board. I'm sorry. I'll be a while before I get back to that. Okay. Now, number 11 is the same circuit. The only thing I've changed here is I've changed the value of R. Oh, I'm going to pick R for critical damping. Draw. I'm going to pick R for critical damping. If you want to see this problem worked out, it's done in the slide solutions. I'm going to skip it because I will bore you to tears if I try to do 6 of these problems today, or I will just drive you crazy. I'll drive myself crazy. So here's another one. This is done in the slide solutions. If you want to see other examples of that, there's one in the audio review notes also. Okay. Same thing here, same value of circuits, and I'm just going to do this, yay, it's still series. I'm going to do this in bamboo paper because I like it better. And I've got all my numbers written down so I don't have to flip back and forth so much. Okay. I look at my R's and L's. The first thing I've got, I want to calculate alpha and omega, step 1. We're starting a method here. And it's series. If it was parallel, they're different equations. So alpha equals R over 2L. 100 ohms over 2 times 5 henries gives me 10 neppers per second. Omega naught gives me is 1 over the square root of LC. And I plug in those values and I get 20 radians per second. And then I've got here that omega naught is greater than alpha. So this is under damping. And we've already gone to step 2, and step 2 is the type of damping. So step 3, I basically have to find the form of the solution. What do I have here? I don't have anything here because I'm at home. Okay. Step 3, form of solution. We're still solving for IL of t. So that's what I'm going to be put here, IL of t. And I'm going to go back to my PowerPoint and look this up because I don't remember these because I don't use them that much. I use a whole bunch of other stuff. And I'm just not a linear systems person. For an underdamped system, yes, My formula solution, A1 cosine omega dt, A2 sine omega dt, e to the minus AT. So I go back and write that down. A1 cosine omega dt plus A2 sine omega dt, all times e to the minus alpha t. Now looking at that, I've already got alpha. I don't have omega d. So I've got to figure out what omega d is. Find omega d, S1, S2 as needed. There is not an S1 and S2 in that equation, so I'm not even going to bother to try to find them. I could calculate them, but that's I don't need them. And omega d is, what the heck is omega d? It is the square root of omega naught squared minus alpha squared. So, square root omega naught squared minus alpha squared. We've already solved for alpha and omega naught. I plug them in, and what do I come up with? Omega d is 17.3, and the proper units are radians per second. Okay, so we got those two. Now, the next thing would be step 5. I need to get those initial conditions so I can solve for A1 and A2. Now, for the current through the inductor, my initial conditions I'm going to care about are IL of 0 plus and DIL dt at t equals 0 plus, which we can figure out from that formula sheet is actually the voltage, the initial voltage across the inductor divided by the inductance. So I go back to my PowerPoint. Oh, where are we at? Right there. And it tells me that IL of 0 plus is ½ amp. Here's the circuit I have to solve. Do I have it written down in here? Yes, I do. Oh my gosh. I'm so proud of myself. Here's the circuit I have to solve to get the initial conditions. I've got a resistor, and it's 100 ohms. I've got an inductor, plus this side. It has a ½ amp flowing through it. We are given that. That's my IL of 0 plus. And I have a capacitor with my VC of 0 plus is defined, and it's a minus 100 ohms. Okay, so we've got IL of 0 plus. It's a ½ amp. Now we have to find the voltage across the inductor. This is the part everyone misses up. Very common mistake on the exam. I won't say everyone. So pay attention. It's just simple circuit analysis. Series circuit, ½ amp through the inductor means I have a ½ amp flowing into the resistor. ½ amp flows in this side. Positive side is down. That's passive sign convention. I've got a ½ amp through 100 ohms. This is going to give me 50 volts. Then I'm going to use, all I've used so far is Ohm's law and series have the same current. Series, same I, and Ohm's law. Now I'm going to use KVL. And going around the loop, I hit a plus, so that's a downward thing. Minus 50, minus VL. I'm hitting plus first all the time. Minus negative 100 is plus 100 equals 0. And that gives me my VL of 0 plus. And that is positive 50. So this is 50 over my inductance, which was 5, I believe is still true. Number 12. Yeah, we'll just go with 5. Yeah, 5. So this DIL of 0 plus, DIL t equals 0 plus equals 5. So we solve for this part and we solve for that part. Next thing I'm going to do is I'm going to go to those equations for an underdamped. Yes, thank you.
50 over 5, wouldn't that be 10?
Yes, you're right. I'm not even looking at my notes, and that's why, because my notes that I did this is 10.
Thank you.
Okay. I may have made a mistake on here. No, I didn't. Okay. So now I go and I look for the equations for A1 and A2 underdamped. Under D, underdog. You guys don't know about underdog. That was my generation. PowerPoint. PowerPoint. So I go back to those key slides, and it's an underdamped system. Now this says V, but I'm really solving for I. I'm not going to worry about that because this is a differential equation. I'm going to replace these V's with I. So IL of 0 plus is A1. No, of course not. And we've already solved for IL of 0 plus. It's half an amp. 0.5 amps. And then the other equation, I'm sorry, is the derivative of the current at t equals 0 plus is minus alpha A1 plus omega d A2, which explains where the minus sign comes from. Minus alpha omega d. Minus alpha A1 plus omega d A2 equals IL prime at 0 plus. And we've solved for that one too. That one was 10. Now we've got a number for alpha. Alpha's 10. We've got a number for A1. That's just beautiful. It's 0.5. We've got a number for omega D. It's 17.3. And we've got a number, we don't know A2. But all this equals 10. I don't even have to do 2 equations and 2 unknowns here. I'm just solving this equation for A2. And I get, when I do a little bit of algebra, I get A2 is 0.867. So that's what we get out of this step. We get numbers for A1 and A2. I'm done. All I have to do is grab the form of the solution, and plug in what I know. Plug in to the form of the solution. So IL of t equals A1 cosine omega dt plus A2 sine, omega dt e to the minus alpha t. We've got A1. And you probably have it written down right in front of you. A1 is 0.5. 0.5 cosine, and omega d was something, 17.3. My decimal points are having trouble with them. 17.3 t plus A2. Oh, wait. We have a number for that. I do have an eraser tool. Go back. No, just do that. No. Here, can I move you guys out of the way so I can do this? Yes. No, I don't want the color. Oh, just do that. Okay. A2 is 0.867. Now I have to move you guys back up. Okay. 0.867. This is why whiteboards are superior. Sine of 17.3. There's a decimal point there. That's a decimal point. T times e to the minus alpha t, and our alpha was 10. And it has units of amps. So we are done. We have done 2 problems today. We've spent 45 minutes doing it. It doesn't go much faster in class. So let's go to the next example, and that was number 12. We did that one. We did the series RLC. This is yet another parallel RLC circuit. If you're interested, the solution is in the slide solutions. Remember where we got there with these series circuits. What we found was that we went through, we did the differential equations, we assumed a solution of the form A e to the st. We said A e to the st cannot be 0. The characteristic equation cannot be 0. This is the characteristic equation for a series circuit. It's going to look a little bit different when we do a parallel circuit. That's why pretty much the only thing that changes when we go to parallel is the fact that now alpha is going to equal, I'm trying to do this smoothly, 1/2 RC. Parallel. And for series, alpha is R/2L. That's an L. Okay. That's the only thing from an engineering perspective that's going to change. Okay. Now we're going to solve a couple of parallel RLC problems. The biggest thing that changes is the value of alpha. The other thing that changes is how you analyze this circuit to get my VC of 0, my VL of 0 plus, and my IC of 0 plus. That circuit analysis is going to change a little bit too when we go to a parallel circuit. Now, every single one of these is underdamped. My damping is, we just did this. 1 over 2 RC. I always look it up. My damping factor is 1 over 2 RC. And remember, we have this thing going on. If alpha is greater than omega naught, we are over damped. Alpha equals omega naught, we're critically damped. And alpha is less than omega naught, we are under damped. That's under, close enough. UN, under. Okay, so if R is increasing, alpha is decreasing. And if alpha is decreasing, I'm getting more towards under damping. So a bigger R here is going to give me a smaller alpha, and it's going to look more under damped. So this is A is the 50 ohms, and C is the 10.5 ohms. As I decrease that in resistor value, I get less under damped. So with a series RLC circuit, if you want to get closer to critical damping from under damping, you decrease the resistor. With a parallel, you're going to increase the resistor. Slight change, but just how you twiddle things in the lab. Right, this is what changes. Alpha is the big thing that changes. The other thing that changes is if I still know this, I know B0 across the capacitor, and I know, yeah, you're doing this again, and I know the current through the inductor. Okay, since I'm a parallel circuit, everything has the same voltage. Which means if I know the voltage across the capacitor, I know the voltage across the inductor, and I know the voltage across the resistor. The thing that I may need to find is the current through the capacitor. Once I know the voltage across the resistor, I'm going to use Ohm's law to find the current through the resistor. Now I've got two currents. I've got the current through the inductor, the current through the resistor. I'm going to use KCL, not KVL, in this case, which is the sum of the currents leaving the node equals 0, to find the last current. And that last unknown current will be IC. Yay, we get to do this in lab 2, yes. Okay, coming up next week. Okay, so we're going to do a parallel RLC example. We're going to skip the first one. The first one is, drumroll please, it is underdamped. The second one's critical damped. We'll do this one. We haven't done a critical damped one yet. So we're going to go through the same thing here. I've got new numbers. I've got a 12.5 millifarad, and I've got L is 5 henries. We want to find R for critical damping, because I want my system to settle as fast as it possibly can. I still have to skip a lot to do this in 3 days. I don't know how I used to do this in the past. Okay, so for critical damping, I'm going to go back to my thing that I can actually draw in. This is number 18. That's how it's number one. First thing I want to do is we're told it is critical damping. So I know it's parallel, which means alpha equal and critical damping. So alpha equals omega naught, which means 1 over 2RC equals 1 over the square root of LC. You ever have to guess what the resonant frequency of the circuit is? It's 1 over root of C. The circuit, okay. We plug in our, we want to solve this for the value of R where this is true. So I do a little bit of algebra and I come up with R equals 1/2 square root of L over C. And I plug in the numbers that I've got and I get R equals 10 ohms. Okay, we found our R for critical damping. We know it's critically damped. Well, this was part 1. Part 2, form of solution. Yeah, that was part 2. 1 and 2. That's part 2, as I labeled it before. Part 3, the form of the solution for critical damping. I go back to that key slide and I look it up. What the heck am I solving for? I'm solving for VC of T, is what the problem asked me to solve for. And the form of the solution is A1 plus, it's A2 plus A1 T times e to the minus alpha T. Okay, we've got alpha. There's nothing else left. I don't have to solve for S1, S2, S3, S1, S2, S1, S2, and omega D. I don't need them. So I can skip that step. Yay. Now I've got alpha. The next thing is A1 and A2. To get A1 and A2, I've got to find VC of 0 minus, or VC of 0 plus, and the derivative of VC at 0 plus. So now we're on to step 5, VC of 0 plus, and dVC dt at 0 plus, which is going to be, we can go back and look at that equation sheet, or we can use I equals C dV dt and come up, this is going to be IL of IC of 0 plus over C. So we look at our circuit, it's parallel, 10 ohms, 5 henries, with an initial current of 8 amps that was given. My IL of 0 plus was given. My VC of 0 plus was given. It's pointing up, and it was 40 volts. No, I didn't want that. Okay, so we've got to do our circuit analysis here. We're given the voltage across the capacitor. Since it's parallel, they have the same voltages. So that's telling me my voltage across the resistor is also 40 volts. Passive sign convention tells us that current, that if the signs are right, current goes into the positive terminal. So if I want, I'm going to use Ohm's law to calculate the current through the 10 ohm V equals IR, I equals V over R, V over R is 4. I don't have to change the sign because I did passive sign convention. I equals IR equals 4 amps. Yeah. Now I've got 2 out of 3 currents. I can use KCL. The sum of the, and passive sign convention puts that down. Also, the sum of the currents on this node right here is got to equal 0. So I've got 4 going out, plus 8 going out, plus IC going out, all has to equal 0. I get IC of 0 plus is minus 12 amps. Okay. We got that number right there. We got the IC of 0 plus. All we have to do is divide it by C. And did I do that? No, I didn't. And C was, it's minus 12. Millifarads. So we've got the initial conditions that we needed. We were given VC of 0 plus, and that was 40 volts. Okay, now I've got to go back and look and find the equations for A1 and A2. Equations for, in this case, we're critically damped. So I go back to my PowerPoint, 18. You can tell this is just throws me. I love transistors. I love the second half of this class. Critically damped. V0 is A2. The derivative is A1 minus alpha A2. So I got those. Do I have them written down here? Yes, I do. Thank goodness. So I won't have to memorize them. So VC of 0 plus is 40 volts, and that also equals A2. So we got A2. The other, and this one doesn't involve a system of equations either. dVC dt at t equals 0 plus equals IC of 0 plus over C, which was minus 12. Yes, over 12.5 milli. $12.5 milli, and milli is my shorthand for times 10 to the minus 3. So that equals A1 minus alpha A2. We've got a number for A2. A1 minus, we had a number for alpha, did we? It was 4. And A2 we just solved for, 40. So we solved that equation for A1. And what do we get? Minus 800 amps per second. That's a pretty big change in current. So we got, oh, that would be, A1 would be volts per second, because it's dV dt. All right. We have numbers for A1 and A2. We're going to plug these into the form of the solution, and we're done. So remember, our form for our solution was VC of t equals A2 plus A1 t times t times our variable e to the minus alpha t. So VC of t, we've got a number for A2. A2 is 40 minus A1, or it's plus A1, and A1 was negative, minus 800, times t, t's are variable, e to the minus alpha, and alpha was 4, t, it has units of volts. Wow, that was impressive. What the heck? Okay, go back to the paper. That was what I was trying to do. There we go. So there's a critically damped. We've done an underdamped, an overdamped, and a critically damped all today. That's a lot. You get to do a couple of these on your homework. No, this is just going to be just fun. Where am I at? Oh, at least it has the numbers on there. So that was, my PowerPoint's going crazy again. We did this one. We're going to skip this one. This is another underdamped one. It's just parallel. And we get right about here. Remember those key slides. What I do when I print them out, or just have them open on your screen and use them when you're solving these problems. This homework, the next homework, not the one that was due today, that was homework 2. That wasn't bad. If you think the homeworks are bad, you should try 380. Okay. Basically, your homework has it has 4 problems on it. The first 2 are fairly simple. The third one, you're solving for, it's a series RLC circuit. The fourth one is a parallel RLC circuit. So you get to do 2 of these problems on your homework. And I think that's fair. On an exam, these are too long of problems to grade for an exam, so I typically break it up into pieces. I will give you like a couple of the steps in the problem, maybe steps 1 through 3. Basically find alpha and omega naught, and tell me what type of damping it is, and tell me the form of the solution. That might be one problem. The next problem is given alpha and omega naught or R's, L's, and C's, and you're told it is underdamped, critically damped, or overdamped. You're told which one of those. Tell me what the form of the solution is. Solve for A1 and A2. That might be a good problem. Another good problem might be given a parallel or series circuit. Knowing VC and IL, solve for VC, solve for IC and VF. So you may have to go through and do that circuit analysis part of it. Yeah, so there's all kinds of like little parts of this that I can test you on. And that's what I usually do. And I'm at my good stopping point. Any questions? What we're going to do, yes, there is more. What we're going to do next class is also going to be on second order circuits. I can show you a little bit of a preview. I've got 10 minutes, but we may just leave a little bit early. What's going to happen here is you don't know the initial conditions. So you have to find the initial conditions. You're not given these anymore. What you have to do is draw the 0 minus circuit draw, oh great, I'm back to my finger again. Draw T equals 0 minus circuit to get VC of 0 minus equals VC of 0 plus. And I'm frozen. And to get IL of 0 minus equals IL of 0 plus. I'm frozen, so I'm just going to leave it here today. If you have any questions, I'll stick around and answer them. I just cannot change anything on my screen. But I can talk to you. Let's see who's here. And which means I cannot read the chat. The chat is invisible to me right now. Austin Arnis, are you here?
Yes, I'm here.
Yay. Elena, are you here? Peter Schoen.
Yeah, I'm here.
Okay. Timothy Singleton.
Timothy Singleton is here.
Okay. And Brendan Wagner. Okay, so the only people missing are Elena and Brendan. Everybody else is marked here. If you have any questions, let me know, and I'll stick around for a few minutes.
There is actually one question on the chat that says for the exam, when you say 1 page of a note sheet, is that front and back or no?
Yes, front and back. And if you want to take my key slides and reduce them down to maybe like 1/4 of a page each, you could do that and print them out.
Sounds good. Thank you.
Okay.
I had a question.
Mm-hmm.
On your keys, are you able to go to your key slide number 20?
I can't look at any. My screen is frozen.
Oh, so but just to remember, so when you're like you have VCO to the negative, is it the same as the ICO negative thing?
No, the VC of 0 plus is the voltage across the capacitor at time t equals 0 plus. IC of 0 plus is just the current through the capacitor.
Okay.
So they're not going to be the same, and you don't know anything about the current through a capacitor at 0 plus. Unless you do the circuit analysis. That's why you have to do that.
Okay, thank you.
Anything else? Okay, if nobody says anything, I'm going to restart my computer and I'm not coming back. You can email me if you want anything. I can get my car. I drove to the building. I just didn't stay for very long. Okay, I will see you guys on Wednesday, maybe in lab. Okay, bye.